Hello, welcome to ChemBio and to A-Level Chemistry revision. This is part 2 of Shapes of Molecules and VSEPR theory. Stay tuned. So in this video we'll continue looking at molecular geometry. This is part 2. If you haven't seen part 1 then please do so. The link is in the top right hand corner right now. So as a bit of a reminder from last time, let's have a look at VSEPR theory, which states that electron pairs are all negatively charged. We all know that, of course, and due to this they repel each other. When we're looking at electron pairs, and particularly in molecular geometry, we're looking at the pairs that are on the outermost shell on the central atom, so that's what we're interested in. Due to this repulsion, the electron pairs on the outermost shell of the central atom of the molecule spread out apart from each other such that they are situated as far apart as possible. Lone pairs, and remember these are the ones that are not involved in bond formation, so they're sitting alone somewhere else away from any bonds, and they repel more strongly than bonded pairs. It just happens to be that they take up more space in 3D. Then the number of the bonded and lone pairs will allow us to determine what the arrangement of these pairs will be around the central atom, and therefore the 3D shape of the whole molecule. And this is exactly what we're going to look at today. We're going to look at several combinations of lone and bonded pairs in different molecules to see what their geometry will look like. Now, I forgot to mention to you in the previous video about something called relative strength, and this is quite simple really. This is what I've just said. Two bonded pairs of electrons, they will repel each other less strongly than if we have a bonded pair and another lone pair, and they will repel each other less strongly as if we have two lone pairs. So if you can imagine two lone pairs side by side, well actually they won't be side by side, they repel each other, but the strength of repulsion between two lone pairs is much stronger than between two bonded pairs. So now let's have a look at all these combinations then. I recommend learning them in table format, and we're going to use the general formulae of different molecules. By that I mean that we're going to have A, which denotes the central atom, and X, which denotes the ligands. Sorry, I did pronounce it wrong last time, it is ligands. Alternatively, for this first situation, we could also have just a simple diatomic molecule. A2 or X2 as well would also work. So this is our first situation, where we have two atoms. There isn't really a central atom because there are only two of them, but yeah, it's either diatomic molecule or just two different atoms together. We're not talking about any bonded or lone pairs at the moment really, because as I said there are no central atoms. So it's quite simple. Common sense really helps us determine that the geometry will be like this. We call this type of geometry linear. The bond angle will be 180 degrees. Now, we don't really have any bonds here, but we still take the value as 180. And a common example of this would be hydrochloric acid, hydrofluoric acid, hydrobromic acid, or any other diatomic molecule, hydrogen, oxygen, fluorine, astatine, you name it. And this is what the geometry would look like. It's basically the structural formula. HCl, there we go. Now let's move on to one central atom and two ligands. So the general formula would be AX2. This time we're going to have two bonded pairs around the central atom. And at the moment, in this first part of the video, we're not going to look at molecules that have lone pairs. We'll do that a bit later. So the geometry would look like this, where we have our central atom in the middle and the ligands either side. This is also a linear geometry, and we also have an angle of 180 degrees. A common example would be CO2, carbon dioxide, and we would show the geometry like this. Now, every time we have a bond angle, we always have to show it on a diagram very clearly. 180 degrees, it's the angle between the two bonds. Now be very careful here, because as you can see, carbon dioxide has double bonds. You know this from the previous videos. Surely then, there aren't two bonded pairs, but four in total. Yes, you're absolutely right. And when we look at molecular geometry, we actually disregard this and we say that, okay, one double bond, or even if it's a triple bond, we say that that is one region of electron density. So we ignore the fact that there are multiple bonds there. We just treat it as one accumulation of electrons of this negative charge. And the same rules apply to bonded pairs. So regions of electron density, they also repel each other just like bonded pairs do. So just remember that when we look at molecular geometry, we ignore the fact that there are double or triple bonds. We still treat them as regions of electron density, or we can also still say bonded pairs, that's fine. So now let's look at 3 ligands with a central atom, so AX3. We will therefore have 3 bonded pairs, still no lone pairs, and the geometry will look like this. Also fairly straightforward. You can imagine that using VSEPR theory, we know that this is the only possible arrangement where these 3 bonded pairs are situated as far apart from each other as possible. Now obviously we can turn around this shape, we can rotate it in different ways, that doesn't matter. The arrangement is always the same. The orientation can be different, that doesn't matter. But it is the arrangement of the electrons around the central atom which is crucial. This has a very specific geometry and we call it trigonal planar. Trigonal planar, the bond angle will be 120 degrees. Quite simply, we divide 360 by 3. Why is it called trigonal planar? Well, if you think about it, all of these ligands, they're in the same plane as the central atom. Nothing is coming out of the plane of the paper or out of the screen, or nothing is going behind it. Everything is all at one level. It's all at one plane. Why is it trigonal? Quite simply, if you have a look here, we can form a triangle like this, and that's why we call it trigonal. An example would be BF3, boron tetrafluoride, and we represent the geometry quite simply like this. Always remember to label the bond angle as well. Now you've guessed it, we're going to look at AX4, where we have 4 ligands and therefore 4 bonded pairs, still no lone pairs. And the geometry would actually look like this. We call this a tetrahedral geometry. The bond angle will be, now attention, 109.5 degrees. You'll notice that some of these bond angles aren't what we might expect them to be. We might think that, okay, 360 divided by 4 is 90. No, actually. You can research the physics behind this if you really want to, if you are interested, but this is just the facts at the moment. 109.5 degrees is the bond angle in a tetrahedral geometry. Now, why is it called tetrahedral? Now, when we look at all the names of these shapes of the molecules, we need to think about the actual 3D shape that would be formed if we join all the ligands together to form faces of a 3D shape. So we kind of need to have a bit of stereometric imagination here. I've tried to help you with imagining it here. So if you can see, these are faces of a tetrahedron. A tetrahedron, remember, is just a pyramid which has a triangular base, a triangular based pyramid. We call that a tetrahedron. So it's by joining all these ligands together, these atoms surrounding the central atom, we will form faces of a 3D shape, and whatever that 3D shape is, that will give the name of the molecule's shape. So in this case, tetrahedron, so a tetrahedral shape. An example of this would be methane, CH4. This is what the geometry would look like. Now notice this time we have one ligand, the one hydrogen to the left, coming out of the screen, and the other one on the opposite side going into the screen. Okay, that is the only possible way that those 4 bonded pairs of electrons are as far apart from each other as possible. Now let's have a look at 5 ligands, AX5, same idea, 5 bonded pairs, no lone pairs. The geometry will be quite peculiar, it looks like this. And the name given to this shape is trigonal bipyramidal. Trigonal bipyramidal, and we actually have 2 different bond angles here. We have 90 degrees and 120 degrees. The molecule PF5, phosphorus pentafluoride, will have this geometry, and we will show it like this. The bond angle of 120 degrees will be between 2 fluorine atoms, one of which is going into the screen, one of which is coming out of the screen. This angle here will be 90 degrees, but this one up here will also be 90 degrees too. And finally, we'll have a look at molecules in the form AX6, where we have 6 bonded pairs and still no lone pairs. This one's a bit easier to imagine. This is what the geometry would look like, and we actually call it octahedral. Again, if you imagine if we were to draw a shape in 3D by making faces with all of the atoms joining them together, we would get an octagon. The bond angle would actually be 90 degrees, and an example of this is sulfur hexafluoride SF6, and this is how we would demonstrate the shape of the molecule. the angle of 90 degrees would be between two of the fluorine atoms on either side. And if you can imagine, these four fluorine atoms here, they're all in one plane, so they're all at the same level, they're all horizontal if you think about it. Just the ones that are drawn at the top, they're just behind the screen. The ones that are a bit lower, which are shown using the solid wedge, they're closer to us. If you can imagine, it's just one plane, or if you think of it as a sheet of paper with sulfur in the middle, surrounded by four fluorine atoms, and then physically above the sheet of paper we have one fluorine atom, and then physically below is another one. That's the way to visualize it, really. Okay, now let's have a look at some molecules where we do have lone pairs. Let's return back to AX2, and we'll have two bonded pairs and one lone pair. Remember that lone pairs, they repel more strongly than bonded pairs, so the geometry would look like this, where we have the ligands, they are pushed away from the lone pair, which would be at the top somewhere here, and the bond angle has now been reduced. This shape is called angular. There are other names, for example, non-linear, V-shaped, or even bent. They're all right, but I think angular is used most commonly. Now, the bond angle does vary with this type of geometry, and to be honest with you, I have to say that the bond angle is never exact. It's never the same for every single molecule. We just kind of take, not really an average, but the most common maybe. But in this case, you can just state any angle that is slightly below 120 degrees. I've gone with 118, and that would be correct. An example would be sulfur dioxide. So yes, these double bonds, remember, we treat them as one bonded pair each, so we have two in total. That's our lone pair at the top. We always have to show the lone pair, and of course the bond angle as well. Now let's have a look at AX3, where we have three bonded pairs and one lone pair. And I used this example in the previous video with ammonia. This is what it looked like, remember? And this type of geometry is called trigonal pyramidal. The bond angle will be 107 degrees. And yes, as you know, we used ammonia as an example. Same idea with drawing the geometry. And lastly for today, we will have a look at AX2, and this time we have two bonded pairs and two lone pairs. This shape is also called angular, or V-shaped, or bent, or whatever, but this time our bond angle is 104.5 degrees. A common example is water, H2O, and this is what it would look like. Now, if you were to think about it, if we have a look at a molecule which has four bonded pairs, like from a few slides ago, its bond angle would be 109.5 degrees. If we then turn one of those bonded pairs into a lone pair, we reduce the bond angle to 107, so we've reduced it by 2.5. And then if we substitute another one of those bonded pairs with another lone pair, well, we get a bond angle of 104.5, which is 107 minus 2.5 degrees. So it just happens to be we have a little bit of a pattern here whereby the lone pairs reduce the bond angle by approximately 2.5 degrees. Now this is not always the case, but you can use this little rule to work out the bond angles for tetrahedral, trigonal pyramidal and angular geometries. That does work. So as a bit of a summary then, remember that multiple bonds are treated as one region of electron density. These regions also repel each other, just like electron pairs. Same rules apply. Now we can also use all these rules to find the geometry of ions. It's pretty much the same idea. It's just remember that whenever we have a dot and cross diagram, we always draw brackets around and then show the charge of the ion. Well, we do exactly the same. When we show the geometry. Just be mindful with ions, whenever you're drawing the dot and cross diagrams, ions are either lost or donated from a different molecule. And that's where sometimes in dot and cross diagrams you'll see that some of the electrons are actually shown with other shapes like triangles, and you might be thinking, what is this random triangle doing here? Well, it's actually an electron donated, or transferred is probably the better word to use here, from a completely different molecule, and therefore the molecule that you've drawn as a dot and cross diagram would have gained a negative charge, and that's why you have to draw around brackets and put a minus sign. Just be careful when you're doing that. The textbook and the specification do recommend us to learn the geometry of some common ions, and here are some other ones as well, and I do recommend memorizing them or learning them at least, because you never know, they might be very useful in an exam situation. So that is it for molecular geometry. If you have any other questions or queries regarding this topic, please do ask questions in the comments. I will absolutely reply to you. Next time we're going to carry on with this topic on bonding and structure, and we'll start looking at electronegativity and polarity. Thank you very much for your attention. Thank you very much for liking and subscribing. See you next time. Goodbye.